In this video, I'll be talking about conservation of momentum and the charts we can use to show that. Remember that a change in momentum occurs because of an impulse. Impulse, in fact, is a change in momentum. And that impulse comes about from a net force times the amount of time it's applied for. We can also write that as the sum of forces times time. But what about the case when our net forces are equal to 0? In that case, we always know that the impulse is equal to 0. And if our impulse is equal to 0, that tells us that our number p is used to express momentum. Our initial momentum is equal to our final momentum. Now, something that comes out of Newton's third law is that if I act on object A acts on me in an equal and opposite way. How can this be used to look at the conservation of momentum? Let's take the case where car A is heading straight towards car B. When they crash, we certainly know that there'll be an impulse or a change in the momentum for both A and B. Why is that? Because A is going to experience an unbalanced force from B, and B is going to experience an unbalanced force from A. If we're assuming that they're traveling along a level road, then gravitational force and normal force are going to be balanced. As I draw the interaction diagram, let's say for A, and I end up enclosing that, I can certainly see that there are going to be three forces. Going to be gravity, normal force with the road, and normal force from the other car. Let's go ahead and we'll draw this a little bit differently, and we'll see what unbalanced forces are acting on this.
Much more of that.
Okay. Okay. But now instead of defining the system as A, I'm going to end up we're going to say that our system is A and B. So we really only have our normal forces down. Sorry, our normal force is up and gravity down. In this case, forces are balanced. No matter how hard these two cars hit each other, the forces are balanced. Remember, it's only unbalanced external forces that change the momentum or are affected by Newton's second law. And in this case, the forces are balanced. We can use that to our advantage. Because the net forces are 0, our initial momentum is going to equal our final momentum. And our initial momentum is going to be the mass of A times the velocity of A initially, times the mass of B times the velocity of B initially. Remember, we'll have to be keep track of which is positive and which is negative. At the end, our final momentum is going to be the mass of A times the velocity of A final, plus the mass of B times the velocity of B final. Let's see if we can put this into a graphic format. Let's go ahead and plot the initial momentum. We've modified this circumstance just a little bit, where we end up seeing, hey, we got our cars, we've given it numbers. So the mass of car A is 300 kilograms, and it's proceeding to the right at 20 meters per second. Mass of B is 200 kilograms, heading to the left at 40 meters per second. So let's map the initial momentum. Okay, so for A, you can say, and I'll put this in 100 kilogram increments. So we have 100, 200, 300 kilograms, and its initial velocity is a 10, and then 20 meters per second. So as before, that rectangle represents the momentum of A. Let's take a look at B. It has a mass of 100, 200 kilograms, and we go 1, 2, oops, sorry, 10, 20, 30, 40 meters per second. So that's at 40 meters per second. So the area of this rectangle, and notice it's below the horizontal line, so that's going to have a negative momentum because momentum has direction. Now the area for this, 300 kilograms times 20 meters per second, is going to give us 6,000 kilogram meters per second. Let's take a look at the at this. We have 200 kilograms times minus 40 meters per second, so the area of this is minus 8,000 kilogram meters per second. So our initial momentum is minus 2,000, that'll indicate to the left, kilogram meters per second. Our sum of forces, even though there's a violent collision here, the sum of forces is 0 because all those violent forces are internal forces. The only external forces are gravity pulling it down and normal force from the road pushing up. So we know our final momentum will be the same as our initial momentum. We're going to add one other condition in here, and that is after the crash, the cars stick together. This is known as an inelastic collision, so inelastic. That's when our objects stick together. What's special about that? That tells us that our velocity, our final velocity for A and our final velocity for B will be the same. So really we can treat the two as a single object. Okay, let's start doing that. So our object now is going to be a 500 kilogram lump of metal. So we'll pattern that out. 100, 200, 300, 400, 500 kilograms. Let's see what our velocity final is. We know that our our momentum is minus 2,000 kilogram meters per second, and our mass of the combined cars is 500 kilograms. So we get minus 4 meters per second. So we'll go 1, 2, 3, about 4 there. So the area here represents the final momentum of the both cars together. Our initial momentum, minus 2,000 kilogram meters per second. Our final momentum, minus 2,000 kilogram meters per second. Initially it was one car going to the right, another car going to the left with more momentum. And in the end we just have both cars together going slower to the left. So momentum is conserved. Even though there's a violent crash and bang and all that, the momentum before equals the momentum after because we picked a system where the forces were balanced and there were no external unbalanced forces. Here we're going to go another kind of like reverse of the situation we saw before. We have two carts, a 2 kilogram cart and a 3 kilogram cart. They're initially at rest with a spring that's compressed between them. You can see that they're at rest. The spring is released and we have the velocity of B moving to the right at 4 meters per second after the spring is released. What's the velocity of A? Okay. If we pick so we have our situation is both of these carts, we can take advantage that our net forces are equal to 0. But let's see what we can do. Okay, our initial momentum, cart A and cart B can be thought of one, or they can be thought of as individual pieces. So cart A is 2 kilograms, but has no velocity. Another way of marking it is that. Cart B is 1, 2, 3 kilograms. Okay, but again, no velocity, so our momentum is 0 kilogram meters per second. Afterward, let's take a look at this. To count for A, it's at 2 kilograms, but we don't have a velocity yet, so let's kind of mark that here. And B is 1, 2, 3 kilograms, so that's B. We also know that's moving to the right at 4 meters per second, so 1, 2, 3, 4. Let's take a look at the area there. The area of that rectangle represents the momentum of B after the spring is released. What we do know is that the momentum of A is going to have to be the same value as this, but the opposite direction. Let's see what this value is. Okay, we know it's at 4 meters per second times its 3 kilograms, so momentum of B to the right is going to be 4 times 3, 12 kilogram meters per second. A, we know, is 2 kilograms wide, so we're going to have a velocity of 12 kilograms meters per second squared divided by our 6 kilograms. It's going to, whoops, sorry about that. Pause that. 2 kilograms tells us that the velocity is going to need to be minus 6 meters per second. So 1, 2, 3, 4, 5, 6. Notice that A is below the line. Okay. If we add up those areas, this being positive area, this being negative area, they'll cancel. So our initial momentum is equal to 0. Our final momentum is equal to 0. So what's the velocity of the cart? Because two things. One, the momentum minus 12 kilogram meters per second, and the minus indicates that it's going to the left. And what is its velocity? 6 meters per second to the left.